Hello everyone, welcome back to this series on trigonometry featuring college algebra. We are still squarely in the college algebra portion, so we'll get into it today, and we're going to be talking about the transformation of functions, specifically talking about vertical and horizontal shifts, vertical and horizontal stretching and compression, reflections about the x-axis, the y-axis, and the origin, and how that might also relate to even and odd functions. So we'll start by talking about vertical shifts here. So if we start with some given function f of x, and we're going to be looking at an example here where f of x is just our basic parabola here, just x squared, that we might call our parent function. If we want to find some new function, perhaps called g of x, well, we can just build that from our old function. It just says take f of x, and here we're going to add some value k to it, where k is a positive constant, and the result will be to shift the entire graph up by k units. So the way that I'm thinking about this is, f of x is an output. We're going to look at the outputs and then add k units to it. So let's see this in action here. I've got the graph of f of x equals x squared already on here. And so if I just maybe write this, we'll keep this in blue here. What this is saying is that this is x squared plus 2. So you can see that we're going to compute whatever x squared is and then add 2 to the result. We will find the output and then add 2 to it, which means that every point should be shifting up. All of the outputs should be shifting up by 2 units. So let's just look at a couple of points here and just see if we can't follow them around the graph. So I'll start by looking at the point 0, 0. We know that the input is 0, the output is 0. So if we then try to take a look at g of 0, so my input will be 0. Well, what will my output be? Hopefully it makes sense that it should be 2, because we're going to start at the output of 0 and add 2 to it. But let's just verify that that is what we get here. So I know that g of 0 should be f of 0 plus 2. Well, if I look at this, 0 squared plus 2, we already know that f of 0 is 0, but just to be explicit, we're writing 0 squared plus 2, and this gives us 2. So I have an input of 0 and an output of 2, which means that my new point will be right up here. All right, let's do the same thing. We'll just grab another point. It's helpful to usually have a couple of points to try and follow around here. So let's look at this point 1, 1 here. So the boxes on this grid are by 2s. So this is the point 1, 1. And so we know that the input of the parent function is 1. The output is also 1, because 1 squared is still just 1. So let's see what happens if we follow this point around. So let me switch back to yellow, and we'll use that to draw this new graph here. Let's look and see what happens to g of 1. Well, that means we're going to take a look at what happens at f of 1, and then we're going to add 2 to whatever output we get there. So 1 squared is just 1. We will add 2 to that, and that should take us up to 3. So the input here is 1 for g. The output is also is 3 in this case. So if I'm looking at 1, and then we'll go up 3 is right here. We could do the same thing with negative 1, and we would see that it would also be up at 3, since negative 1 squared is positive 1. We'll add 2 and get 3. So now we have this new graph that looks something like this. And it is very similar to our original graph of x squared, but everything has been shifted up by 2 units, because again, we're just looking at the output of f of x, adding 2 to it, which makes all of the outputs move up 2 units. So let's do the same thing here with, let me switch to a different color. Let's do the same thing here with this next function. H of x is equal to whatever f of x was, and then subtract 3 units off of all of those outputs. So we'll do the same thing here, where we will follow a couple points around. And so if I'm trying to find what h of 0 is, well, that's going to be the same thing as f of 0, and then we're going to subtract 3. Well, we know that f of 0 is 0, or I could write explicitly by just plugging into what I've written above. 0 squared, which is f of 0, minus 3 is negative 3. So I have an input of 0, and I have an output of negative 3. So we will put this down here. We'll move this point 0, 0. The output of 0 is moving down to negative 3. And I can do the same thing with h of 1 here. This is saying, okay, take a look at what f of 1 was, and then subtract 3 off of that. So this will give me 1 squared minus 3, which is 1 minus 3, which is negative 2. So that means that at 1, I've got a point here at negative 2, and same thing on this other side here. If I plugged in negative 1, I would also get a result of negative 2. So now we've got, well, let me try that a little bit better here. Now we've got this new function that, again, looks very similar to the parent function of x squared, but now everything is shifted down 3 units. And I should have, I meant to write explicitly what this was. Let me just move those down a little bit. That this is equal to x squared minus 3. So let me just create a little visual separation here. So there we have it. We have the new functions here of x squared plus 2 and then x squared minus 3, resulting in a shift of 2 units up or a shift of 3 units down. So there are our vertical shifts. I think that that can be somewhat intuitive if you are grasping all of those concepts there. Next, we're going to take a look at horizontal shifts. And the idea is somewhat similar, but a little bit of the intuitiveness kind of tricks us here. But the idea is same thing. We're going to look at the same function here for a lot of these examples, is that if we are given some function f of x, so again, we're looking at f of x equals x squared, and we're given a new function. So now instead of looking at the output and adding or subtracting some value, here we're adding or subtracting some value from the input before we actually find what the output is. So if we're given some h value that is positive, and here we are doing f of x minus h. Well, this is going to result in a horizontal shift to the right, which is maybe a little counterintuitive, since when you subtracted things in the last example, they moved down, which I think is intuitive. When we added a value, it moved up, which I also think is intuitive. Here, the intuitiveness is backwards, and so that is something to just keep in mind as you're working on these. I think getting these patterns down is good, and just remembering that these ones work a little backwards than how you might expect, and we'll see that in a couple of examples here. So again, if we're given f of x minus h as our argument here, then that's going to result in a shift to the right, which is the positive direction, but in a sense we're kind of undoing the fact that we subtracted off that h. And then similarly, if we add some value of h to the input before we find the output, that is going to result in a shift to the left, which is technically the negative direction, but it is in a sense undoing the adding of h that we put on. So that always helped my mind of thinking about how shifting the maybe opposite way of what we would expect is undoing what we had made as our adjustment in the input here. All right, so let's take a look at this example here. We have f of x equals x squared again. So we'll just chase some points around again like we did earlier and kind of see what happens. So let's start by looking again at 0, 0 here, and we can kind of see what happens as we adjust our inputs as we go. So if I'm looking at, let me switch back to yellow, and let me also just explicitly write what our new function is going to look like, because since we're subtracting 1 off of the input before computing the output, that means that we need to subtract 1 off of our input of x, and then apply our function, which is squaring the entire thing when we're done. So the result here is x minus 1 quantity being squared. So this is what we're going to look at here. So if I want to find out what happens to this point 0, well, that's going to be the same as f of 0 minus 1. So we should get the same output at f of negative 1. If I look at f of negative 1, that is at positive 1. So you can already kind of guess that this might get shifted over here. But let's just verify that for sure. So if I am plugging this into our explicit version here, what we're going to have is 0 minus 1 being squared, which is negative 1 squared, which is positive 1. So we have an input of 0 and an output of positive 1. And it looks, maybe right now, like our graph is still shifting up, but we will see that actually what happened here is that this point shifted to the right by 1 unit. So it's not entirely clear yet, which is why we typically want to use a few points to see what happens instead of just focusing on 1 point. So let's see what happens if I plug in g of 1. So we're looking at the original point here. Oops. Yeah, this point here at 1, 1. And if I plug in g of 1, well, that's going to be the same as f of 1 minus 1. So we should get the same thing as f of 0. And f of 0 was down here. So we should hopefully see that here, and I think that we will once we do 1 minus 1 being squared is 0 squared, which is 0. So this is telling me that I have an input of 1 and an output of 0. So input of 1, output of 0. So really what happened is this point shifted over, the vertex of this parabola shifted over 1 unit. And then we could do the same thing with 2, and we would see that we would get another point here, and what happened there was this point being shifted over 1 unit. So you can see that the points that we're looking at are not exactly maybe what we expect once we shift things over. So that our new graph will look something like this. Now, when you're graphing these in your homework or whatnot, it's not that you have to work all of this out. I'm doing this at this point just so you can like visually see, like literally as I'm plugging in points, what the new graph looks like. And I could just go plot a bunch of these, but I'm hopefully convincing you that, okay, yes, even though that I am subtracting 1 off of the input, the result is a shift to the right. I'm kind of undoing that that subtraction of 1 by moving it in the positive direction. So there is a little bit of counterintuitiveness there, like I said. So let's take a look at this next one here. We have h of x. Let me make a visual separator just so things don't get too smushed together. But what we're saying here is I want to add 2 to the input before I compute the output. So what we have here would be x plus 2, and then the function f of x is to square it when we're done. So this is what our new one will be here. So again, we can chase some of these points around and see that maybe we're not seeing precisely where each point is going, but we can get the general shape here as we go. So if I plug in g of 0, or I'm sorry, I want to do h of 0 in this case. I've changed my variable names, or my function names. Well, this is going to be the same as f of 0 plus 2. So this should give us the same output as f of 2. H of 0 and f of 2 should be exactly the same. So in this case, if I plug it in explicitly to our formula here, we're going to get that this is, what am I doing? 0 plus 2, all being squared. So 2 squared gives us 4. So we have an input of 0 and an output of 4. So an input of 0, so I'm looking for the point 0, 4 essentially, which is up here. So it might look like maybe the vertex has shifted up, but truly what has happened is this point over here shifted to the left by 2 units. So we will keep trying a few other points here and verifying that, okay, that is happening to all of these points as we go. All right, so let's chase another point around here. So I know I've been plugging in 0 and 1, but to keep things on the graph here, let's maybe plug in h of negative 2 and see what happens. So this should be the same as doing f of negative 2 plus 2. So the result here should be the same as f of 0, which I know should be 0 from the previous graph that we have here. But the result that we should get is negative 2 plus 2 being squared, which says 0 squared, which is just 0. So what this is saying is that if we have an input of negative 2, we have an output at 0. So an input of negative 2 will give us an output at 0. And then if we wanted to plug in, say, negative 4, we should get another point up over here. And we can see now that our entire graph has shifted over to the left by 2 units. So, moral of the story here is that things move maybe counterintuitively to how you might expect, but hopefully by plugging in some points here, you can at least be convinced that that is the way that things move. So just to kind of recap the shifts here, if you're adding some value to the output of the original function, well, that's going to shift it up. If you are subtracting some value from the original function, at the output of the function, that will shift it down. If you are subtracting some value from the input before applying the function, that's going to be a shift to the right. And if you are adding some value to the input before applying the function, that'll be a shift to the left. All right, next we will talk about vertical stretches and compressions. Sometimes I call that stretches and squishing, so if you hear me say that, I mean compressions. But here, still given a function f of x, we want to find a new function, but here we're going to multiply some positive value a by the output of each function, which will result in either a vertical stretch, and it will stretch if that value that we're multiplying by the output is bigger than 1. So if you think about, you get some output of 2, you multiply it by 3, which is bigger than 1. Well, now you have 6. That output has stretched up by a factor of 3. And then similarly, if that value a is between 0 and 1, so it's still a positive number, but now it's a fraction between 0 and 1, which means if we had some output value of, let's say, 10, and then we multiply it by 1/2, well, now it has compressed back down to 5. So let's look at an example here and kind of see how we can manipulate the graph that we are starting with. So here we have f of x equals x squared again. If I'm looking for some new function, g of x, well, this would be 2 times x squared. So what this is saying is, you know, find whatever x squared is, and then multiply it by 2, which means all of our outputs will be multiplied by 2, which means we're going to stretch them up by a factor of 2. So let's just kind of see explicitly what happens here. Maybe uninterestingly, if I look at g of 0, well, this gives me 2 times 0 squared, which is still just 0. So we notice that this point actually stays in the same spot. But maybe let's take a look at g of 1, which is going to give me 2 times 1 squared, which is 2, which means at 1, we did have the point here, but it has been stretched up to 2. And we have symmetry here, so we'll get another one on this side. And maybe we'll just do one more here. If I'm looking at, let's say, g of 2, this is going to give me 2 times 2 squared, which is 4. Well, that's going to go up to 8, so I'm off the graph at that point. So at 2, that's going to go like way up here. So we're getting this stretch of our function by just kind of taking it and pulling it up like that. So that 2 didn't work out for me because it ended up being off the graph, but hopefully that still makes sense that we're getting this stretch in that regard. All right, let's take a look here that if this a value that we're multiplying here, it's still positive, but now it's some fraction between 0 and 1. So we've got 1/3 f of x, which means we're going to take all of our output values and multiply them by 1/3, which means they're going to be compressed by a factor of 1/3. So let's take a look at some values here. If I want to, again, take a look at h of 0, well, same story as before. Not too interesting because 1/3 times 0 squared is still just 0. So we are still going to get, what color am I doing here? I should have done yellow or something. So we'll say that this is in yellow. And now this point is still right here. But let's grab some other points that we can take a look at. Let's do h of 1. So this is going to give me 1/3 times 1 squared, which is 1/3. So if I'm looking at h of 1, instead of being at 1, 1, well, now it's going to be down at about 1/3. And since this is symmetrical, we'll get another one on the other side here. And maybe let's take a look at what happens at, well, let's do 3, since that will work out kind of nice. We'll look at h of 3. And this is going to give me 1/3 times 3 squared, which is 1/3 times 9, which is 3. So we have an input of 3 and an output of 3. So that means we're at 3, which is over here. Using symmetry, we can get a similar point over at -3. And now graphing this, we see that this thing has been compressed by a factor of 3. So you can imagine just pushing all of those points down by a factor of 1/3. I said 3, but by a factor of 1/3. So this is vertical stretching. And again, it kind of has that intuitiveness when we were applying some value to the output of the function before we were maybe adding a number or subtracting a number, and that made a shift. Here we're multiplying by a number, and that number is either bigger than 1, which corresponds to a stretch, or that number is between 0 and 1, some fraction, and that results in a vertical squish. And I think that intuitiveness is still there, where we're just taking the output and we're either stretching it by multiplying it by a big number, or squishing it by multiplying it by some fraction, some positive fraction. Next, we'll look at horizontal stretches and compressions. And again, just like when we did horizontal shifts, there's kind of this bit of counterintuitiveness where maybe things move in the opposite direction of what you think. But here, instead of multiplying the outside of the function, the output of the function by some value, we're going to multiply the input by some value and then compute whatever that output was going to be. And this will result in a horizontal stretch or compression. So in this case, if that b value is bigger than 1, well, that's going to give us the compression. So that is maybe opposite of what we saw before. And similarly, if that b value is between 0 and 1, some fraction, then that's what's going to stretch it horizontally by a factor of 1 over b. So that is kind of the inverse of what's maybe would be intuitive here. So again, we will look at our friend f of x equals x squared, and we can chase some points around here and see what happens. So what we've got going on is that I can write this as 2x being squared. So here I'm multiplying the input by 2 and then squaring it once we're done. So if you just grab some points here, so we will look at the vertex here, which is always kind of an important point on a parabola. So we'll see what happens with this. And I don't think that we'll find anything too surprising, since g of 0 is going to give us 2 times 0, all being squared, which is just 0 squared, which is 0. So they have a common point here at the vertex. Well, let's see what happens to 1. If I do g of 1, this is going to give me 2 times 1 squared, which is 4. So I have an input of 1, I have an output of 4. So that's going to be there. We can use symmetry and we'll get a point here on the other side. So it almost looks the same as a vertical stretch, but here what we have is a horizontal compression. And you'll notice that as these things move around, they won't look so similar. There is some more to see than maybe what is showing up in these simple graphs. So there we go. We have a horizontal compression in this case, since the input, the value that we're multiplying by the input is bigger than 1. All right, let's take a look at what happens if we make this 1/3. So here we're looking at some h value. Again, h of 0 is still going to just give us 0. So if I look at this, this would be 1/3 times 0 being squared, which is still just 0 squared, which is 0. So again, we have this common point at the vertex where nothing too interesting is happening. But let's take a look at h of 1. And what this is saying is we're going to multiply 1/3 by 1 and then square it. And this is going to give me 1/9. So at 1, boy, we're going to be way down here at 1/9. And then same thing over here on this side. And maybe let's look at something a little bigger, just to get some more interesting values on here to help us build the shape here. Let's look at h of 3, because I think that might do something nice for us. So looking at that, that's going to give us 1/3 times 3, and then we're going to square it. So this is just 1 squared, which is 1. So what this is saying is we have an input of 3, we have an output at 1. So we can mark that point here. And then by symmetry, -3, I'll also have this point here. So here we can see that we are making a horizontal stretch of our original graph. And that is because the value that we're multiplying the input by is still positive, but between 0 and 1. So again, these are patterns that you're hopefully recognizing, and you can use them as you're sketching graphs, and hopefully plugging in some points here, at least convincing you that things are happening the way that I'm saying that they're happening. All right, next we'll take a look at reflections. So starting with some function f of x, and here I've changed our example to be, instead of f of x equals x squared, I have f of x being equal to the square root of x, because this will give us something a little bit more interesting to look at once we start reflecting about some axes here. But what we're looking at is if I want to build some new function, well, I could just apply a negative to the outside here, which means that we're going to figure out whatever our output is, and it's just going to make it negative. So if it was positive, it'll make it negative, which is going to result in a reflection about the x-axis. So if I was going to get a result of 4 up at 2, well, then I would just flip it over to the other side here. And we'll take a look at that a little more carefully here in just a second. And then similarly, what this is saying is, well, let's just take a look at making the input negative and see how that affects the output. And we will see that that's going to result in a reflection about the y-axis, meaning that instead of plugging in -4, we're going to plug in, instead of plugging in +4, we're going to plug in -4. Things will simplify and we'll still get the same output as we did at +4. So that would result in a reflection about the y-axis. So let's chase a few points around here and see what's going on. So here we're saying we'll build a new function by just looking at the opposite of our original function, the opposite output values. So if I want to look at g of 0, so I think that we'll find nothing too interesting going on here. G of 0 is going to be negative f of 0, which is -0, which is still just 0, so we still just get this point at 0, 0. But let's take a look at g of 4, which is the same as negative f of 4, which is negative square root of 4, which is -2. So that means that my input is 4, my output is -2. So just kind of like I had said before. Maybe we can also take a look at g of 1, just to get another point on here. So g of 1 is going to be the same as negative f of 1, which is negative square root of 1, which is -1. So at 1, we get an output at -1, and we can see that we're getting, oh, that wasn't my best connecting of the dots. Try that maybe one more time. But we're getting something that looks very similar to what we started with. It's just been reflected about the x-axis. So I know that we're changing the output values, which sometimes, we correspond with the y-axis. So again, there's a little bit of counterintuitiveness about which axis this is reflecting. But I think it does make sense. If we're looking at some output value and then making it negative, well, it's going to send it to the other spot, the other output value. And if it started out being negative, well, then it would just send it back to being positive. So there we have a reflection about the x-axis. Now we'll look at a reflection about the y-axis. So here what we're doing is not adjusting the output values, but adjusting the input values before applying the function. So if I wanted to take a look, h of 0 is still going to be not that interesting, because this says, okay, let's take a look at f of -0, which is still f of 0, which is still 0. So again, we've got, let me choose a different color here. We'll pretend that I did that in yellow just to keep things the same here. And let me get rid of, just move this out of the way. Well, we'll put it over there for now. Okay, so let's take a look at maybe h of 1, which is going to be the same as f of -1. Uh-oh, we're in trouble, right? Because that would be trying to take the square root of -1, which we don't get. So as it turns out, 1 is not part of the domain here. So maybe instead of looking at h of 1, we could look at h of -1 and hopefully get something nice. So let's take a look at h of -1, which normally wouldn't be part of the domain of our parent function, because we can't, again, take the square root of a negative. But once I do this, this is the same as doing f of -1, because we're putting another negative in front of the input before we compute the output. So this is saying, okay, find me f of 1, which is the square root of 1, which is 1. So I have an input of -1, I have an output of +1. So -1, +1, and let's do something similar, and I'll just have to maybe do it above the graph here. So let's take a look at h of -4, which is the same as f of -4. Again, we are forcing in another negative. That is what we have here. So this is saying, find me f of 4, which is the square root of 4, which is 2. So this is saying at an input of -4, we have an output of +2. So at -4, we have an output of +2. And if I graph this, it will look something like that. Well, let me try that one more time and see if I can't get it a little bit better. Nope. Something like that, which we can see is a reflection of our original, this time about the y-axis. So there they all are together in one spot, the blue being our original function. If we make the output values all negative, that's going to flip everything down to the negative side of the graph. And if we make all the inputs negative, well, that's going to flip everything to the negative input side of the graph. So here we will put it all together. We can see we have an example here called f of x. There's going to be some horizontal shifting, some vertical shifting. There's going to be a reflection, I can see because of the negative in front. And then since I'm multiplying the outside also by 1/2, I can tell that there's also going to be a vertical squish here, a vertical compression. So in the instructions here, it's asking us to graph. We're going to start with the base graph. So the base graph here, maybe I'll call that, or sometimes I call that the parent graph. We'll call it the base graph here. The base graph, I'll call it b of x for base graph, is going to be just our standard old x squared graph here. So let me just get that on this graph, and then we can go from there. So I know that 0 squared is 0, 1 squared is 1, 2 squared is 4, -1 squared is +1, and -2 squared is +4. So here is our base graph, or our parent graph, and it looks something like that. Okay, so now we will apply some of these modifications that we're making here. And the first thing that we want to do, I know that we started this lecture by talking about vertical and horizontal shifts, but what we actually want to do is focus on this guy in front first. So before we get to the shifting, which is sometimes the easiest part here, let's look at dealing with this squish and this reflection and see what we can't get here. So we'll switch colors and we'll do the next part in green. So again, in the instructions here, and you might see something like this in the homework from my class, that you need to kind of do each piece of this transformation one at a time, so you have a bunch of the transformations happening on the graph. I'm okay if you combine a few of these, but if you try and do too much at once, it's really easy to get the wrong thing. And we're being asked to at least look at 2 points as we move things around, because as we saw, especially with some of that horizontal compression and squishing, it kind of, sometimes it's hard to tell, is this a vertical thing, is this a horizontal thing? And having a couple points to help chase things around will be helpful. So the first thing that we're going to do here, as I said, is look at this -1/2 of x squared, which means that every point here is going to be squished by a factor, compressed by a factor of 1/2, and then flipped across to the other side here. So what that's saying is, if I look at 0 as my input, well, I will square that and I will multiply that by -1/2, and I still get 0. So we're going to keep this point here. If I look at 1, well, what's going to happen to this guy? Maybe I don't want to put that in, but maybe I'm looking at what's going to happen to 1. Well, it's going to get squished by a factor of 1/2, and then it's going to get flipped to the other side of the x-axis. And same thing with -1 over here. Once I square that, it's going to be +1, and then I'm going to cut that in half, and then I'm going to flip it to the other side of the x-axis. And then I can look at these points here. So this is at 2, +4. Well, that 1/2 says that I'm going to compress it down to 2. So my output of 4 became 2. And then I'm going to bring it over to the other side, flip it to the other side of the x-axis. So we'll get that point there. And then same thing with this point at -2, +4. We're going to cut it in half. That's multiplying by the 1/2. And then the negative portion of that says to flip it across the x-axis. So it will be down here. So this is the function that I've written in green, which isn't quite everything that we want yet. But let's see if I can't get this to look not so terrible. Here is our kind of intermediate form of the -1/2 x squared, which has been a reflection across the x-axis, and we've also squished this thing vertically by a factor of 1/2. All right, in the next step here, let's deal with shifting this thing horizontally. And since this is x plus 3, what that means is that we are going to shift it to the left by 3 units. And the horizontal portion is usually the more counterintuitive bit. So what we'll be doing in this next step is negative 1/2 x plus 3 squared. So that means that every point here that I've looked at is going to get shifted to the left by 3 units. So in the instructions it said to chase 2 points around. I've got 5 points here that I'm looking at just so that I can be extra sure. But what this is saying here is that this point that I've x'd is going to move over 1, 2, 3 units. This point is going to move over 1, 2, 3 units. This point is moving over 1, 2, 3 units. And then same thing with this guy, 1, 2, 3. And this guy's moving over 1, 2, 3. So here is getting one step closer to the final answer. Here I've shifted the graph over to the left 3 units. And then the last thing we want to do here is make this final shift of moving everything up by 2 units. So the final form here, negative 1/2 x plus 3 squared plus 2 means I want to take this blue graph that I have and shift all of those points up by 2 units. So we're going to take this guy and move him up 2, or them up 2. We're going to take this guy and move it up 2. So that one's in between. So that one felt a little weird, but I got that straight, I think. We'll move this guy up 2. This guy's moving up 2. And then 2 there as well. So the purple dots are the final form. The X's were just me kind of keeping track of stuff. So again, the purple's the final form here. This is what we were asked to find in the very beginning. We just did it step by step. We kind of did the reflection and the vertical compression at the same time. And then we did the horizontal shift and the vertical shift. And sometimes doing that horizontal shift and the vertical shift at the same time can also be not too bad. But here I just split it up so that we could kind of get a little bit more practice there. All right, and we will finish this off by talking about even and odd functions. So the function, or a function is called an even function if for every input x, f of negative x equals f of x. And what we're going to notice there from a graph, that means that the graph is symmetric about the y-axis. And so we already had talked about some things about symmetry over the y-axis, and it is even functions that have that sort of symmetry. And then we'll also look at odd functions, and this says something similar, and it says that for every input x, if I make the input negative, it will also make the output negative. And the graph of an odd functions are not symmetric about the x-axis. If they were, we wouldn't have a function. You can think about that. But it will be symmetric about the origin. So at first, we're just going to kind of get some practice plugging things in and seeing how we could compute this from equations. And then on the next page here, we will look at the graphs of these examples that were given to explicitly see their symmetry here. So let's take a look at this first one here. We have f of x is equal to x to the 5th plus x. And so we want to determine, are these functions even, odd, or neither? If it doesn't satisfy either of these definitions above, then the function is neither even or odd. Functions don't have to be either. It doesn't mean that they're not functions or something. It just means that they're not even or odd, and they don't have some of this nice symmetry that we could use later. So what this is saying is, and I kind of like to write this down, that if this function is going to be even, then what we would get is that f of negative x is equal to f of x. And in that case, we should get that f of negative x is equal to x to the 5th plus x. We should get exactly back what we started with. And if this function was going to be odd, then f of negative x should equal negative f of x, so negative x to the 5th plus x, which is negative x to the 5th minus x. So what we're going to do is actually compute what f of negative x is, and we'll just see if we either get the same function back or if we get the opposite of the function back. And I've explicitly written those down above so that we can make an easy comparison. So now if I'm just literally plugging in negative x everywhere I see an x in my original function, then this is going to give me negative x to the fifth plus negative x. And if I simplify from here, well, remember that if you raise a negative value to an odd exponent, the result will still be negative. So the result here is still negative x to the fifth. Oh, I forgot my negative on this one. I wanted to add negative x there. And then adding a negative is the same as subtracting. So this gives me negative x to the fifth minus x, which is one of the proposed things that we had here. So this is an odd function. And we will see on the next slide that we should see that it is symmetric about the origin. So that is how to compute from an equation if we have an even or an odd function or neither. So we'll look at the other examples here. So again, I think it's nice to explicitly write out if this function is going to be even, then g of negative x should just give me the original function back, which is 1 minus x to the fourth. And if it is odd, then g of negative x would be negative our original function, which if I simplify that a little bit, gives me negative 1 plus x to the fourth. So at this point, we will plug in, we will actually compute what g of negative x is and see if we get any of these proposed equations back. So if I do 1 minus negative x to the fourth, so again, everywhere I see an x in my original function, I'm just replacing it with a negative x. And if I raise a negative number to an even power, the result will always be positive. So that means that this is the same as 1 minus x to the fourth, which is what we started with. So that means that this is an even function, because making the input negative has no impact on the output, meaning that we have an even function. And we'll see on the next slide that this means that we are symmetric about the y-axis. Okay, finally we have this last function, h of x equals 2x minus x squared. So let's just again explicitly write out if this function was even, then that means that making the input negative should give us the original function back. So that means that we would get 2x minus x squared back. And if this function was odd, making the input negative should give us the negative of the function back. And if I simplify that, I would get negative 2x plus x squared. So let's take a look here, and we will actually compute what h of negative x is. So that just means everywhere I see an x in the original function, I'm just going to replace that with a negative x and then simplify and see what we get. So 2 times negative x gives me negative 2x. And then we've got minus, and we talked about that if we have a negative value being squared, being raised to an even value, then the result will be positive. So this gives us x squared here. And that minus in between is still this minus in between here. So this, well, now we've got it simplified, and just looking above, do I see negative 2x minus x squared? Well, it's not that one. So we don't get the same function back. And here we have an addition symbol separating these two terms. So it is neither. We have neither an even function or an odd function, because making the input negative does not either give us the same function value back or the opposite function value back. So here is how we can find even and odd functions from their equations. If we want to look at the graph, so here's the same examples here, but I've listed the graphs. We know from the first page here that this first one is odd. And this says that if I make the input, I'm sorry, I'm looking at the wrong one. If I make the input negative, the output should also be negative. So if I'm looking at taking an input of 1, well, I should be able to find another value symmetric throughout about the origin at -1, -2. So we've made the input negative and we've made the output negative, and we find a spot that's still on the graph at that point. So here we are symmetric about the origin, and just like I drew that line through there, I can find a corresponding point for every value that just goes straight through the origin like that. This next one here is even, that we saw on the last page. And again, this means that if I make the input negative, the output should still be exactly the same. So here I have an input of -1, the output is 0. Well, if I make the input -1, the output is still 0. And you can see every point here, if I just look across the y-axis, this is symmetric about the y-axis, there is another point that has the negative input value that has the exact same output value. So here we have an even function. And then finally, we can see that this last one is neither even or odd, because if I look at this input value of 1, 1, well, there's nothing that is symmetric about the y-axis. So making the input negative did not keep the same output, so this is not even. And we did not find a value symmetric through about the origin here, meaning if we make the input negative, we didn't get the negative version of the output. So here we have, we have neither odd nor even. So either based on the equation or based on the graph, we can see if these functions are odd or even. So from there, I'll leave you to practice. I wish you luck, and I will see you next time.